Hello everyone, we are Team 9, known as Q Engineering. We are proposing the production of acrylic acid by oxidation of propylene. Our team consists of me, Adila, Pangkang Ying, Zulfadli Najihah, and Siti Hajar.
For our presentation outline, we will go through process overview first, followed by heat integration, followed by process control, followed by process safety, and lastly profitability analysis. As a recap, we have chosen the production of acrylic acid from propylene as our main process. The raw material will be propylene and air. Meanwhile, the main product will be acrylic acid and the side product will be acetic acid. The reaction is called two-step oxidation of propylene and we will be using molybdenum ferrum bismuth catalyst for our reactor. This is our process flow diagram before heat integration. As you can see, air, steam and propylene will go through a mixer before it enters our reactor. After that, the stream will flow into our flash column. The gas from the flash column will flow into a membrane separator before being released as off-gas and wastewater. Meanwhile, the liquid component from the flash column will flow through an extraction column to remove the water content. Lastly, the stream will flow into two separate distillation columns before it goes out as a product. Next is heat integration. To do this, all of heating and cooling utility is tabulated, and from that, our composite curve, problem table algorithm, and grid diagram can be done. Composite curve is one of the way to do the heat integration. The graph in the screen right now shows our composite curve. Initially, the cold composite curve was above the hot composite curve. Since it is impossible to proceed with the heat integration, the cold composite curve will be shifted horizontally until it is located below the hot composite curve. A delta T min of 10 degrees has been assumed, meaning that there is a 10 degrees temperature difference between the hot and cold composite curve after the cold composite curve has been shifted. From the graph, the pinch temperature can be seen at around 170 degrees Celsius. Another method of heat integration is by using problem table algorithm (PTA). At the highest temperature, the enthalpy change indicates the minimum heating requirement. Meanwhile, at the lowest temperature, the enthalpy change indicates the minimum cooling requirement. As you can see, the enthalpy change with the value of 0 indicates our pinch temperature, which is at 170 degrees. Heat exchanger network is the last part of heat integration, where a heat exchanger will be added to integrate the heating and cooling requirement. Since our heat capacity for hot stream is higher than cold stream, the below pinch design can be done. The heat from stream H2 can be recovered by the cold stream C3. And then the remaining cooling requirement for stream H2 can be done by using additional cooler, while the remaining heating requirement for stream C3 can be done by using an additional heater. The table shown in the slide is our potential utility saving after the integration of the heat exchanger network. It can be concluded that our potential saving for hot utility is at 81.43% and our potential saving for cold utility is at 6.73%. This is our process flow diagram after the heat integration. The diagram shown in the green outline indicates the additional heat exchanger being implemented into our process plan.
Now we move on to the process control. The figure shows our overall PNID for the production of acrylic acid. I will explain the process control installed at each of the major and minor equipment involved. Firstly, air is compressed from 1 bar to 6 bar. Anti-surge controller is installed at the compressor to prevent from surges, reversal of flow, and compressor damage. During extreme conditions where the pressure at outlet stream deviates from set point, anti-surge controller helps to maintain minimum flow through compressor and handle the surges. The raw materials, which are propylene, compressed air, and steam, is set at a fixed ratio of 5, 25, and 70. This will be controlled by a ratio controller at the mixer. The flow rate of compressed air and steam will be manipulated to ensure the desired ratio is achieved, as our main raw material is propylene. In the fluidized bed reactor, the reaction is highly exothermic. Therefore, flow rate of molten salt as cooling medium is adjusted to achieve the desired temperature. Pressure controller and alarm is also installed where flow rate at outlet stream will be adjusted if set point is not achieved. As the last line of safety measure, a pressure safety valve is installed at the reactor to avoid from over-pressurization or vessel rupture. At the flash column, a flow controller is installed to monitor the inlet flow rate. Steam as heating medium will be supplied to the column and regulated by a temperature controller. A cascade controller where pressure is the master and flow is the slave controller is installed. As the pressure deviates from the set point, the flow rate will be adjusted at the outlet valve. Another cascade controller where level is the master and flow is the slave controller is also installed. As the level of column deviates from set point, the bottom outlet flow rate will be adjusted accordingly. For membrane separator, pressure is an important variable as the liquid gas mixture vaporizes as off gas. If the pressure deviates 5% from set point, the high or low pressure alarm will be activated and the valve at the top outlet stream will be adjusted accordingly. For extraction column, the inlet flow rate, which is stream 14 and 17, will be controlled by flow controller. The temperature of extraction column is regulated by adjusting the steam supply. The liquid level will be regulated by level controller. The high level set point is at 80% to avoid flooding and 5% to avoid drum drying. If the level deviates 5% from set point, bottom outlet valve will be adjusted. For distillation column, the temperature of bottom stream S23 is controlled by manipulating the steam supply to reboiler. Pressure of distillation column is adjusted by the flow rate of cooling water supply to condenser. Level controller is also installed at reflux drum to avoid overflowing. The level of distillation column is controlled by level and flow cascade controllers, where the bottom outlet flow rate at stream S23 will be adjusted if the level of distillation column deviates 5% from set point. As last line of safety measure, pressure safety valve is installed to protect against rupture of column. For pump, the flow rate at S24 is set to 28,000 litre per minute to ensure the desired outlet pressure can be obtained. If the flow rate deviates plus minus 5% from set point, the control valve will be adjusted. A gravitational decanter is used to separate diisopropyl ether from water, hence no process control is installed. The water will be further treated as wastewater, while the diisopropyl ether will be recycled back with a ratio of 9:1. A ratio controller is installed to ensure only a fraction of diisopropyl ether is recycled and the other fraction is treated as wastewater. For coolers, temperature controller is installed to achieve the desired temperature at outlet stream S3. Flow rate of cooling water is adjusted if temperature deviates 5% from set point. Similarly, for heaters, temperature controller is installed to achieve the desired temperature at outlet stream S9. Flow rate of hot oil is adjusted if temperature deviates 5% from set point.
For process safety, we are doing HAZOP CHRA standard operation procedure for plant startup and shutdown and also the plant layout. For our group, HAZOP have been done for all major equipment and here we highlight important parameters for each equipment. For fluidized bed reactor, pressure is very important to be controlled and HAZOP have been done by us in two situations, either low pressure or high pressure with causes and consequences. For the safeguards, we have listed out all the control systems that have been applied in our plant, which pressure alarm system and pressure relief valve. And our recommendation is to make a bypass or backup control valve and make regular inspection and maintenance for the equipment. Same situation with flash column, but with different parameters which is level. Most of the parameters can give same causes, but the consequences may result differently. For example, pressure may over-pressurize and rupture the column if too high, and level can cause flooding in the column if too high too. For the extraction column, we are using flow parameter. However, since flow does not have alarm system, so we added in the recommendation for installing the alarm system. Membrane separator also using pressure parameter. And for distillation column, we are using temperature parameter. Common causes are blocking and leaking piping and also valve malfunction, which affected all the parameters in the system. CHRA, also called as Chemical Hazard Risk Assessment. We are focusing our feed and main products which are propylene and acrylic acid. After our assessment, this is the result of our CHRA. We are referring from safety data sheet and also CHRA textbook. For propylene risk rating can be moderate and level of risk is low. And we added control measure and organization control in Form D and Table D2. For acrylic acid, since this is our main products, so the amount of the chemical that can be exposed to people are very high. So we are doing CHRA for acrylic acid to assess the risk of this chemical. As you can see, here is the control measure and the recommendation which is recommended by the company that provide the safety data sheet. They are suggesting to separate the combustible item from the chemical and wear PPE while handling the chemical. Next is SOP of the plant startup and shutdown. This is our procedure. I want to highlight in startup plan procedure is to focus on tightness test, which is to check valve, piping and equipment is in good condition and does not have any leakage or blocking in the stream. For shutdown procedure, we are highlighting the depressurizing unit and drain out every chemical first to prevent dangerous hazards such as explosion.
So now I will be presenting about the plant layout. This is the plant layout of our alkalic acid production plant. Basically, our plant separate into three areas. The first area is the safe area, which consists of office, canteen, medical facility, laboratory, parking and fire station. The second area is start from the back entrance, which consists of most of the storage area like scheduled waste storage, raw and product storage, warehouse and loading and unloading areas. This zone is specially designed only for lorries and truck to have easy access for all transportation work using the back entrance and exit. Last is our production area, which mainly consists of process area and nearby facilities like hot and cold utilities, wastewater treatment plant, compressor room, control room, and also maintenance workshop. There are some justification for our plant layout, like emergency water pond standby beside the fire station. Gather area with ferns is well guarded to ensure the safety of production area. Sufficient exit is provided in this area. Hot and cold utility is separate with the wastewater treatment plant to prevent effect by each other. Wind direction is also determined to prevent the emission blow to the safe zone, which is the first zone.
So moving on to chapter 5, Profitability Analysis. This is our total bare module cost calculated for each process equipment. As you can see, the most expensive equipment is fluidized bed reactor with $35 million, followed by flash column. From the CBM calculation alone, we can deduce the higher cost is due to higher volumetric flow rate and higher operating pressure, since the equipment is used as the first part of the process. In addition, we try to keep compressor and pump as low as possible to minimize the CTBM by assuming motor efficiency at 90%. Overall, the CTBM for this plant is $81 million. So next, here showing calculation bare module cost for reactor. The assumption for resident time is 5 minutes and ratio length to diameter is assumed to 3:1. Since operating pressure at 6 bar and temperature 175 degrees C, which is below 500 degrees C, we had chose carbon steel as the precursor material. So basically from the assumed resident time, we can calculate the reactor volume. Later, we can find the internal diameter and length of the reactor vessel. Overall, CBM for the reactor is $7 million. However, we multiply the CBM with 5-unit reactor. This is due to higher total volumetric flow rate, which result the internal diameter, DI, and length are bigger than the recommended size range, as stated below. Thus, the total volumetric flow rate here has been divided into 5. So overall, that is why the reactor CTBM is much higher than the others equipment. So moving on, this is the utility cost for wastewater treatment. Basically, the liquid waste generated from the canter and extraction column, with water as the main component to be discharged. So from the calculation, around 1.2 million cubic meter liquid waste per year, with cost utilities factor USD 0.33. So we can get the volume for wastewater treatment cost around USD 428,000 annually. Next, moving on to the allocated capital investment for the utility plant. Based on our assumed size factor and the previous wastewater treatment, the total investment around USD 244 million annually for the utilities plant. Next, the section for labor costs. Assumption is that operation around 300 days or 44 weeks per year with 12-hour working time and 1 shift per day. Workers are given 3 weeks of vacations per year and sick leave. So here, table summarization for labor costs, estimate around 60 workers including inside and outside operation. The salary based on our reference reading, overall allocate around USD $558,000. So next, these are the profit margin. Assumption for catalyst around 1% of the total raw cost material. So calculate profit margin simply total product revenue minus raw cost material. So based on the material market price, it was deduced USD $993 million for annual profit margin.
Now I will be presenting for total capital investment. As you can see from the top of the table, the first one will be total bare module cost, which is 81 million, will be summed up with site cost, building cost, off-site facility cost to become total direct permanent investment cost. Then the CDPI will sum up with contingent cost to become total depreciable capital cost. And the CTDC will sum up with cost of land, cost of plant startup to become total permanent investment cost. Finally, the total permanent investment cost will sum up with working capital to become total capital investment cost, which is CTCI, with a amount of 676 million. For the total production cost of our alkalic acid production plant will be 1,479 million, which major will be occupied by our raw material cost with 962 million and utility cost with 244 million, and with some of other costs, which is labor operation cost, maintenance cost, tax, depreciation, and general expenses. And then this is our cash flow analysis for our plant. So in the first column will be the total capital investment cost, which I mentioned earlier in previous slide, which is 676 million, will be divided into 3 years with the percentage of 50%, 40%, and 10%. And the second column will be the revenue from the profit margin, that slide. And last, the third column will be the operating expenses, which I mentioned earlier in the total production cost. So after we done the analysis, we are able to gain the positive payback start from 5th year onwards. From the graph, we can see that when there is an interest rate of 0%, the project will have a payback period of 5.4 years. This is a relative good result, as such a lump sum of capital can be repaid in such a relative short period. For the discounted cash flow analysis, when other interest rate is taken into account, we can see that the payback period will be prolonged. Different interest rate is taken into account, as it is our duty to assume as much possibility of market change as possible. This helps us to make preparation for the worst and analyze on whether on a high interest rate the project will be still at a good decision to be made. Using interest rate of 5%, 10%, and 15%, the payback period is 6.2, 6.7, and 7.3 years accordingly. This provides us a good indication that even the market tend to change, we are still able to have a positive payback averagely on the 6th year. A normal plant is capable to operate easily over 20 years with good maintenance. The short payback period of only an average of 6 years show that our project is a good investment to be taken. The profitability analysis is done by calculating ROI. The project gives us a positive ROI, which indicates the total return has highly exceed the total cost. Given with a high number of ROI at a payback period of at most of 7 years, our project is said to be very attractive to investor. That's all from our presentation. Thank you.